All right, so I'm Thomas, I'm from Oracle Labs, and I will talk about Truffle, a self-optimizing runtime system. So when we're speaking about runtime systems, we want two things. For one thing, we want generality. So we want to execute a wide variety of languages. On the other hand, we also want to be very performant. So we want to have all language abstractions be optimized away. So no matter how weird the language semantics are, we want, for example, that this JavaScript on the left side is translated to very little machine code instructions, basically directly executed on the machine without having to pay for the additional cost of the abstractions. Truffle is a system that will provide you with both generality and performance. And my talk is now about how to show you how to do that. So let's focus first on the generality aspect. So obviously we do not want to have different runtime systems for different languages. And the previous approach to that is to use, for example, an intermediate format, for example, bytecodes, to separate the semantics of the language from the semantics that are well understood to the runtime system and to the compiler and optimizing part of the runtime system. Truffle uses a slightly different approach where you express the semantics of the language not by generating bytecodes, but you express the language semantics by writing an interpreter for that language in Java. You're writing an AST interpreter. And the Truffle system then uses automatic partial evaluation to derive for the hot parts of the code optimized versions. So there are two obvious advantages of this over bytecode generation. One thing is that the startup performance is a lot better because you do not have the generation step and the bytecodes do not need to warm up before you would be able to execute your AST. The second one is so you would be able to actually express more than just statically bytecodes. So when you're expressing your language semantics in bytecodes, you emit bytecodes and then the bytecodes are kind of fixed and stable. For Truffle, when you're executing an AST, you can modify and rewrite this AST. And the rewriting of the AST, with the rewriting of the AST, you can model the slow pass, fast pass idioms of your language. And you are a lot more flexible than as if you would just have to generate bytecodes for all parts of your language. Another obvious advantage of this is that we have to write less code because you do not need to write that bytecode generator. But the generation of the bytecodes or the generation of the optimized code is automatically derived from the definition of the language semantics. So I talked about that this AST structure is kind of flexible. So it is possible to modify it. It is possible to rewrite one AST node with another one. And this is very handy when it comes to language semantics of dynamic languages. So let's consider how you would implement the semantics of a JavaScript add operation in Java. So usually you would implement it as a rather big cascade of if-else-if statements. Usually that cascade actually would be a lot bigger because you would probably also specialize on string, you have to check for array, and so on and so forth. And the more dynamic the language or the more types your language contains, the bigger and more verbose this if statement is. When we express the language semantics like this and apply partial evaluation to it, then in the optimized version of the code, all the if statements will remain. And the optimized version of the code will still be verbose, big, and potentially slow. So we don't want to do that. And that is why in Truffle, we split up these if statements into separate parts where you would have a specialized version of the operation. For example, for the double case, you would have a specialized version of the operation for the string case, and you would have another kind of specialization for all the other cases. You can see that from the way you specify that, it's actually not much different from above. It's just a bit more declarative. And what we do then is, while we're executing the AST, we will rewrite the operation, the node that does the operation. And we would specialize the node that does the operation. This specialization occurs in a finite state automa, where you start off in an uninitialized state. So in the beginning, your add operation will be uninitialized. And this uninitialized version would check the types of the left and right input on first execution. And based on the types that are used on the first execution, it would then rewrite itself to a node that contains exactly the right level of specialization. So it would rewrite itself to either a double node, a string node, or a generic node. And this kind of rewriting means that later, when we do the partial evaluation, when we do the optimization step of going from the AST interpreter to the compiled code, then we only partially evaluate through the currently active version of the operation. This means that our optimized code only really contains, if there was only doubles on this operation, only the double case. Or if there was only strings in the operation, only the string case. So we do not need to do any kind of code duplication in order to distinguish the different cases. The different cases are encoded in AST nodes that rewrite themselves, and as the optimization step, we partially evaluate through them. So to give you another example of how this AST rewriting really comes in handy, and how this AST rewriting adds a new dimension to the way how you specify your language semantics. And this example is now about an inline cache. So an inline cache in this AST rewriting mode would be at first a node that is uninitialized, meaning this call or this access to a JavaScript field was never executed yet. And only on the first execution, it would replace itself with the type that came in for this execution, with a specialized version for that type. But in case at the next execution this type does not come in again, we would still have the backup of the uninitialized version. So by expanding the AST, we model an inline cache that is flexible. And so in the polymorphic case, we would then chain several nodes after each other. And whenever we think that the chain gets too long, we would replace ourselves with a generic version of that node. And the interesting part about this is not so much that you can do this in an interpreter. The interesting part is that when you then apply the partial evaluation, the kind of code that the compiler generates for you, the kind of code that the optimizing compiler generates for you, exactly corresponds to the way you model your inline cache. So the compiler would exactly model the right if statements, because it would always partially evaluate through the current state of the inline cache. And therefore also the way you model your inline cache is flexible. So you have the ability to make a different inline cache and not only get the benefits for the interpreter from it, but automatically also the benefits from the compiler. Because the compiler itself doesn't even know about the concept of inline cache, still it produces the correct code pattern. There is another thing in Truffle which is important. So we already have now covered that the AST includes the profiling information. The problem with such specializing profiling information is that when you have, let's say, a helper function that is called from 10 different places in your application, the profiling will get very polluted. This is actually also a problem in current profiling in the JVM. And our solution to the problem is that we do not have the notion of hot methods, but we only have the notion of hot call sites. So we would, in our profiling, never think that a certain method is hot. We will only think that a certain call site is hot. And in case that call site gets hot, then it kind of makes sense to duplicate the method we are calling for exactly that call path. So in this case, we have a method down here that is called from 3 different places. And you find out that, but if it's called from this kind of place, it's called very often. So this call site is hot. So what you would do is we would now duplicate this method and inline it into this into this method. And we do this kind of inlining at the interpreter level. So this is a difference to inlining in the compiler, where you would do like this statically and just once when you compile it. Here we do inlining dynamically while we are interpreting. And this kind of duplication we do is not a simple copy of the current nodes, but it puts the current nodes back to the uninitialized state. So this means if you had an add operation, and we were already in the general case, because from one call site it was called with 2 strings, from another call site it was called with 2 ints, it ends up in the generic case. But after we do this duplication, the duplicated version will be in the uninitialized case, and we'll be able to specialize for exactly this call path. This gives us an advantage in case of there is a very deep call hierarchy or for helper methods that might specialize in a better way if they are duplicated. So I'll now walk through an example of how the partial evaluation works. I have now talked a lot about the partial evaluation, and to make this a bit more practical, I have here an example of a small JavaScript function that adds up values, and it accesses an array. And the array, and as well as the count, comes in as a parameter. And in the following slides, I will now show how this JavaScript AST is converted into Java IR. So I will use JavaScript code and Java code to model those 2 entities. And you will find the JavaScript code being in dark red and the Java code being in blue. So when we start the partial evaluation through the AST nodes, the first node we encounter is the node that is the root node of the function that is basically assigning the parameters to local variables. And so I've now replaced parts of the JavaScript method with Java code. And here you can see that the way we pass parameters, it's always just as an object array. This is a very good simplification for the overall system. And given that we do inlining in the AST interpreter already, we should have the most important call site should already have gone away. So this is also not a performance problem. So we have 2 parameters in that method, and we assign it to the local variables of JavaScript. So the next thing is that we replace the local variables of JavaScript with local variables of Java. We specialize the local variables, and we have also profiling for that. So we have, in the same way we rewrite operations, like the add operation I showed you, we are also rewriting local variables, meaning that we specialize them also for int, double, or generic. So in our case, the profiling has found out that, well, the first argument, the array, is of type object, so we can just use object for that. However, the second argument, the profiling has found out that it's always an int. So whenever this function was called from this place, it always gave an int. And in that case, we really model n as a primitive int local variable and cast the argument directly to an int and unbox it immediately at the beginning of the function. Because this was a dynamic kind of check, or we cannot guarantee that this will always be the case, we need to add a check before that, which is a check with de-optimization. Note here, and maybe in difference also to the previous talk, that there is only one version of n here. So we only modeled the version of n that contains the primitive int. This means that if you don't have to duplicate the code, or you don't have to duplicate the local variables for all your specializations. You really only have this one specialization that you have profiled for. If this specialization does not hold, you de-optimize back to the interpreter and later generate a new optimized version. So the third local variables in this example is specialized to double. This means that during the execution of the interpreter, at first this x would have probably been specialized to int, but for some reason it overflowed at some point, which made it despecialized to double. And therefore, we would then have x directly modeled as double. And we don't need a security check for x because it's just assigned a constant. So the next step, we would then encounter the two control structures here, the while and the return. And basically, the partial evaluation would just convert the JavaScript while loop into a Java while loop. So this automatically works. One thing maybe to the local variables. So the local variables in our AST interpreter are obviously modeled as accesses to a frame array. So we would always, in the AST interpreter, have the local variables stored in a frame array, and we have accesses to it. During the partial evaluation, however, we force escape analysis on that frame array, and this escape analysis guarantees that the local variables of our guest language are then, from a compiler's perspective, the same as local variables in Java. So there is no indirection in our optimized code. So yeah, the control structures basically translate one-to-one. And now it comes to the operations. We have three operations in here. We have the greater than 0 operation in here, which specialized on int, so it can just be converted into a Java greater operation. We have the plus operation here, which specialized on double, so it can just be converted to a Java double. And then we have this decrement operation, and the decrement operation can underflow potentially. So we model it as a special AR node in our compiler. I've used it as save decrement kind of function, but in the compiler this would be just one compiler node. And we can then apply in the Graal compiler a special transformation that will allow us to potentially remove the overflow check as part of the static analysis of integer ranges that Java compilers do. So after that, the decrement operation would then also be just a normal Java decrement. So the last part now is actually the most interesting one, and it is the array access. So for the array access, we do a similar kind of specialization as for operations. So we have different versions of the array access for the int, double, and generic case. And so in our case, this was an int array. So it always stored int values, and so we specialized it for int. This means that the array access code is as you can see here, so the array access code is first a check that our optimistic assumption that this is an int array holds. Basically, if it's not an int array, we would go to another case. Similar, where we would go to another case of the add operation if one of the parameters is not correct. We would here go to another case if it's not an int array. So this is again just a check and then a de-optimize. Then we cast it to an int array, and the int array stores as its contents really a Java primitive int array. So there is no boxed values in this int array. It's all primitive values. And we access the content of the array. There has to be an interaction between the array and the content, because in JavaScript, an operation could potentially change the size of the array. And then we also have to include an overflow check. But here we also specialize the operation. Sort of, this was always a JavaScript. So in that case, this was always a JavaScript array access that was always on an int array, and where the access of the int array was always within the bounds of the array. So then this bounds check also becomes into a check and then a de-optimize. And finally, we can then access the actual content of the array using a Java array access. So this now looks a bit verbose, but we can then apply actually compiler transformations to optimize that further, in case there is more than one array access, or in case, as here, there is an array access within a loop. So as you can see here, of course, the first instance of check and the check cast is loop invariant. So we can move it out of the loop. We can go further and then say, OK, this content array, it's not final, but actually, because there was no array access within that while loop that would have assigned to it, so there is no array access within that while loop that would have ever increased the size of a JavaScript array, this is also loop invariant. So we can move that one out of the loop. And then the last one looks a bit similar to a Java bounds check. And we can use the fact that we know the range of n. So n is always between n and 0, and always decreasing. And with that, we can also move this kind of JavaScript bounds check out of the loop, just as we would do with the Java bounds check. And in this picture, we are now exactly at the point where we want to be. So we have converted our JavaScript function into a Java function. It really looks sort of like a Java function. There is a little bit extra casting maybe going on, and a little bit more checks than in an average Java function. But the difference really is very small. And also, most importantly, the most important part of that code, the while loop, looks like a Java while loop. There is no difference. And this is now the point where we give this kind of code to the Graal compiler and let it do the normal Java optimizations with it. And after doing that, the Graal compiler will then convert this Java IR into the optimized assembly that I showed on the first slide. So the loop really is that small and fast. So the most important part here is that we actually do all the transformations that I showed you now on the slides, on a step through. We do them before we hand the IR off to a Java compiler. So this means that we do not need to do fine-tuning on the Java compiler. We do not need to do fine-tuning on the inline heuristic of the Java compiler, for example, or on the boxing elimination. There was no special boxing elimination applied anywhere. I didn't have a slide on boxing elimination. That was intentional. The primitive type specialization avoids the need for boxing elimination. So, and only after we do all these transformations, we hand it off to a normal Java compiler that will then do its normal loop optimizations. So this is the current structure of our system. We use Hotspot to execute the Truffle AST interpreters. And this actually is already kind of a standalone part, because every AST interpreter is written in pure Java and can execute on a normal JVM. And then you have this optional component here that will do the partial evaluation that I described on the slides, that will do these special optimizations for Truffle and At that point, then we hand it off to a normal instance of Graal, where you'd use Graal, just we use it for compiling Java methods. We then use it for compiling this specialized IR. And then Graal is using an adapted version of the hotspot code cache to install the code. We actually can 100% leverage the de-optimization facilities of the hotspot VM, because this partial evaluation means that we would just, for hotspot, it would just look as if we would install a special version of that method. So the partial evaluation, a lot of things are kind of constant and a lot of things are changed in the method, but still we can use hotspot's infrastructure to install that code because it looks just like a special version of that method. So there's a lot of people at the moment involved with that project. There's quite some people at Oracle Labs. There's at the moment also a project starting at Oracle Labs, which is called Alphabet Soup, that is building upon it, and in particular interested in the implementation of J and JavaScript. We also have several academic collaborators. From Purdue University, we have Professor Jan Wittek and Florel Morendon, and they will mostly look into an R implementation. And there's also a couple of students from JKU Linz that try to implement languages on top of it. One of the things we're also experimenting with at the moment is implementing Java in that language, because some of the optimizations I showed, for example, this inlining on AST level, could actually also be interesting for Java. I don't know, many of you are familiar with Cliff's Click's blog entry on the inlining problem, where the wrong type feedback for hotspot is a big problem when you hand in a closure into a call. This problem is solved by AST level interpreter inlining. And in particular, I also want to mention Andreas Wöss, who's actually in the room here, because he did most of the initial work on the JavaScript implementation and prototype and helped shape that framework. So, well, I'd like to welcome anybody to join in on discussions, and in particular also later to join in the workshop from Lucas. And the workshop will actually demonstrate that this is not just slideware, but it's actually in a prototypical state implemented. We will show an example language and how we optimize it. I just heard that the workshop was actually was rescheduled. Yeah, exactly. Okay, so the workshop is fine. Okay, fine. So the workshop is not rescheduled and will be right after the presentation. And well, yeah, then finally, thanks for your attention and yeah, keep asking questions. Thank you.